This is the second video on conditional probability, and we just need to give some more information on two types of events: independent and dependent. Let's write what we mean by independent events. This could be selecting heads after rolling a die. Another example could be selecting a 6 from a die and a spade from a deck of cards. Okay, so dependent, let's pretend we've got some balls in a bag. So selecting red would alter the probability of selecting a red or a blue. Okay, so now that we've defined independent and dependent events, let's have a look at how we prove that an event is dependent or independent. And it's worth noting that on independent events, one event has no effect on another. Selecting a red here definitely has an effect on selecting a blue or a red. Okay, so let's see how we can prove each event. Let's do independent first. The best way to prove that an event is independent is to show that the probability of A and B is equal to the product of A times the probability of B. That is the best way to prove. So another way, you can show that the probability of A given B is equal to the probability of A. Then you also have to show the converse, probability of B given A is the probability of B. You have to use the two of them. And finally, so we've done intersection. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. So how do we prove dependent events? We prove dependent events by using the conditional probability formula. And we can smarten that up and say that the probability of A intersection B is equal to the probability of A given B multiplied by the probability of B. We could also use that the probability of A or B is equal to the probability of A multiplied by the probability of B after A has occurred. Okay, so let's look at some problems. Okay, so the first problem, if you want to pause the video and have a go doing this. Okay, so let's have a look at A. So we've got the probability of blue eyes is 0.35, the probability of blonde hair is 0.15, and the probability that they have blue eyes and blonde hair is 0.1. And we're asked to find the probability of blonde hair given blue eyes. Well, that's simply going to be the probability of blonde and blue divided by the probability of blue eyes. So that's just going to be 0.1 over 0.35, which is roughly 0.29. So B is the reverse probability of blue eyes given blonde hair. So the intersection is going to be the same. The difference is we divide by blonde, which is 0.15, and we get 0.67 to 2 decimal places. Okay, so we need to prove independence. So I'm not going to do all of these. So pause the video and see if we can do some. I'm going to do, let's do, I don't know, D and E. So pause the video and have a go. So for D then, let's find this. It is 0.21, and we are given that A intersection B is 0.21, so we can deduce that this is an independent event. So for E, E is exactly the same thing. Okay, so in which case let's do B. So B says that the probability of A given B is 0.3, and the probability of A is 0.3 also, and the probability of B is 0.6. So the probability of A given B is the probability of A and B all over the probability of B. So if it's independent, this is the probability of 0.3 times 0.6 all over the probability of 0.6. That cancels, and that gives 0.3. And we were told that the probability of A given B is indeed 0.3. So we can say that A and B are independent. So pause the video and see if you can do the rest. Okay, so these are the answers: independent, independent. C is dependent. D is independent. E is let's see. Okay, I'm going to say E is neither. And F is independent. Okay, let's have a closer look at 8E. Okay, definitely neither. Okay. Better description is impossible. So let's have a look at the next question. Okay, see if you can pause the video and have a go at doing this. Okay, so let's have a look. So we've got A. Probability of A union B is the probability of A plus the probability of B minus probability of the intersection. And this is called the principle of inclusion exclusion. So let's fill it in then. We've got 0.4 plus 0.6 minus the intersection, which is 0.4 multiplied by 0.6. That just gives 1 minus 0.24, which gives 0.76. And it's the same for B. Probability of A union B, 0.6 plus 0.3 minus the product, 0.3, which gives 0.9 minus 0.18, 0.72. Now, if A and B were disjoint, and that is that A and B then the probability of A and B will be 0. So that would reduce the probability of A union B to the probability of A plus the probability of B. Let's have a look at the next one. Okay, this one's a little bit more tricky. Pause the video and see if you can have a go at doing it. Okay, so a small committee is formed from a group of 4 boys. So let's look at the sample space. So we've got boy 1, boy 2, boy 3, boy 4, and 8 girls. So we've got girl 1, girl 2, girl 3, girl 4, girl 5, girl 6, girl 7, and girl 8. So the cardinality of this set is going to be 12. The cardinality of the boys is 4, and the cardinality of the girls is 8. So we're asked to find what is the probability that both girls, well, that is the probability of a girl given if at least one of the members of the committee is a girl. What's the probability of girl? Okay, given a girl. So let's find the total ways of choosing two from 12. So the total ways is going to be 12 choose 2, which is 12 factorial, 2 factorial, 10 factorial, 12 times 11 times 10 over 2 factorial times 10 factorial, which gives 66 ways. So let's find the reduced sample space. So out of the 4 boys, we're choosing 0. And from the 8 girls, we're choosing 2. Now we need at least 1 girl, so from the 4 boys we could choose 1, and then from the 8 girls we choose 1. So this represents girl, girl, boy, girl. And we can do this on our calculator to get 60. So let's find the probability of a girl given a girl. Well, that's going to be the cardinality of the reduced event space over the cardinality of the reduced sample space. And I'm going to put that down below, get rid of this. So the reduced event space is just simply going to be 4 choose 0 multiplied by 8 choose 2. It's not a fraction. The reduced sample space is just going to be 60. It's just going to be this here. Okay, so I hope you're happy with how we calculated the reduced event space. So the reduced event space is the probability of getting a girl and a girl. The total sample space is going to be the probability of girl girl plus probability of boy boy. Not the probability, the number of ways of doing it. Okay, so I'm making good progress. It doesn't go. Okay, Jack and Ben have been tracking their success rate of converting goals in rugby. Jack converts 70, so the probability of Jack is 0.7. So the probability that Jack doesn't convert is going to be 1 minus 0.7, which is 0.3. Probability that Ben converts is 0.6. Probability that Ben does not convert is going to be 0.4. And we are told that Jack and Ben have been tracking their success rate of converting goals. Jack convert at a recent home game. They both get a kick, but only one converts the goal. What is the probability that it was Ben? Okay, so we got Ben, Jack, and the probability. So we're told that only one converts their go, so we need to consider all options. So Jack doesn't convert, and Ben doesn't convert. Ben doesn't convert, Jack converts. Ben converts, Jack doesn't convert, and they both convert. So this is the probability of Ben doesn't, Jack doesn't. The probability of Ben doesn't, and Jack does. Ben does, Jack doesn't, and both. So this is going to be 0.4 multiplied by 0.3, which is 0.12. This is going to be 0.4 multiplied by 0.7. This is going to be 0.6 times 0.3. And this is going to be 0.6 times 0.7. So we're asked to find this conditional probability. What is the probability that Ben converts given only one converts? So this is going to be equal to the probability of, let's call this A and B, the probability of A and B all over the probability of B. So the probability that it was Ben, given that only one of them, let's do this in red, is going to be this. Probability that Ben converts given only one of them is going to be 0.18. And the probability that only one of them converts, so that's going to be 0.18 plus 0.28. Going to be plus this. So if we add those together, we get 0.18 divided by 0.46, and that is roughly equal to 9/23. Okay, so let's have a go at doing the last one. Okay, so the last question, let's do it in two ways. And the first way, we're just going to use the traditional method, and the second way, we're going to use our sample space. Okay, so let's define the two events. Let's say that event A is the probability of getting a £10 note, and the probability of B is 20 or more. So how many ways can we do A? Well, let's list the amounts. So we've got 4 5s, 1, 2, 3, 4. We have 3 10s, 1, 2, 3. So some commas. and we got two 20s. So don't forget A is 10, so we can choose one 10 or two 10s. So if we choose in one 10, remember that they choose two notes. We're selecting from the three 10s. If the second one is not a 10, we are selecting from 1, 2, 3, 4, 5, 6. Two 10s, we're selecting from 3 and 2. Okay, on your calculators, you can show that that is 21. Let's consider B. And the cardinality of B. And this is more than 20. Well, if we're doing more than 20, we can select 10 and then we can select a 20, or we can select a 10 and a 10. That's the only way we can do it. So if we're selecting one 10, there's three 10s, we select in one, and then we need to choose a 20. Alternatively, if we're selecting two 10s, there's three of them, and we choose 2. So that is 9. So the probability of B given A is the cardinality of A intersection B over the cardinality of A. The cardinality of A is 21, and the cardinality of B is 9. We can simplify that by dividing by 3 to get 3 over 7. Now you may wonder, this is A and B, and we just inserted a 9. Don't forget B is 20 or more, and we can't make $20 or more without choosing a 10. So this is automatically including a $10. Okay, so let's see if we can do this now using the sample space. So let's define the event. The probability of B given A is going to be the cardinality of the reduced event over cardinality of reduced sample. Okay. And I've drawn a table here. It's without replacement, so if we take out the 5 is going to disappear. Same with the 10, same with the 20. So I'm going to highlight the regions. So we need, let's do the numerator first, which is a 10. So all these are 10s. Pen's decided not to work. So Still no success. Okay, so let's use a different color. So all these are 10s here. And we've got a 10 here. Okay, so we've got 3 multiplied by 1, 2, 3, 4. So this covers this section. We've then got 2 times 3, which covers this section. We have then got 3 1, 2, 3, 4, 5, 6, 7, 8 multiplied by 8. So if we add all those up, we are going to get 42. We now need B, which is 20 or more, and let's circle those. So this is 20 or more, this is 20 or more, this is 20 or more. So there we've got 3 times 3. This is 20 or more. This is 20 or more. Plus 3 times 2. So this gives us 9 plus 6. We can simplify this at the top. That is 15. Over 42. Looks like we're missing something there. We're missing a 3. We get all these. 1, 2, 3. That is 4. I wonder if we're missing something. That is 4 times 3. Which is 12. So that gives 18. Over 42, which is 9 over 21, which gives us 3 over 7. So exactly the same. Okay, so I hope you understood those. The sample space method is a little bit more cumbersome, but it's a little bit easier to understand than using the combinations. So I hope you enjoyed this video and that you continue to practice your probabilities.